You know, there's a reassuring narrative that's become prominent in popular science and space agency communications over the past few decades. The idea that we've finally developed the capability to protect Earth from asteroid impacts, that unlike the dinosaurs who were helpless when a 10-kilometer asteroid struck 66 million years ago, causing mass extinction, we have the technology to detect threatening asteroids years or decades in advance and deflect them using nuclear weapons or kinetic impactors or other methods. That planetary defense is now an achievable goal, and asteroid impacts have transitioned from inevitable catastrophes to preventable disasters that we can address through proper investment and planning. This narrative has been bolstered by successful missions like NASA's DART double asteroid redirection test, which deliberately crashed a spacecraft into the small asteroid moon Dimorphos in 2022 and successfully changed its orbit, demonstrating that kinetic impact can deflect asteroids as predicted, and by improved detection capabilities through telescopic surveys that have cataloged most large near-Earth asteroids, and by international coordination through the Planetary Defense Coordination Office and similar organizations planning responses to potential threats. All of this creates impression that asteroid defense is a solved problem requiring only continued vigilance and modest funding. And I'm going to tell you why this narrative is dangerously over-optimistic. It is impossible to stop asteroid impacts in any comprehensive sense that would actually protect civilization from the full spectrum of impact threats. Not impossible to deflect specific asteroids under ideal conditions with decades of warning and favorable orbital mechanics. We've demonstrated that's feasible in limited cases, but impossible to create reliable planetary defense system that prevents catastrophic impacts across the range of scenarios that threaten civilization, because the detection challenges and warning time limitations and deflection difficulties and resource constraints and political realities and sheer scale of the threat create barriers that cannot be overcome with realistic technology and funding. We can't stop them in the sense that matters for civilizational survival. We might deflect a few specific asteroids that we happen to detect with sufficient warning under favorable conditions, but we cannot prevent all dangerous impacts, or even most of them. The threat remains existential despite our efforts, and understanding why planetary defense is fundamentally limited is essential for realistic risk assessment and for recognizing that asteroid impacts remain unavoidable, disasters that civilization must be prepared to survive rather than prevent. Now, let me be precise about what I mean by impossible to stop asteroid impacts, because there's a spectrum of asteroid threats with vastly different characteristics and defense requirements. Small asteroids less than about 20 meters diameter enter Earth's atmosphere frequently, several times per year, but they typically explode high in the atmosphere, releasing energy equivalent to small nuclear weapons without reaching the ground. These atmospheric airbursts cause little damage, except in rare cases like the 2013 Chelyabinsk meteor, which exploded over Russia, injuring about 1,500 people through broken glass from the shockwave. These small impactors are essentially unstoppable because we can't detect them until shortly before impact, and they're too numerous to track individually. Medium asteroids, roughly 50 to 150 meters diameter, impact Earth every few thousand to tens of thousands of years. These cause regional devastation over areas of thousands to hundreds of thousands of square kilometers. An ocean impact creates tsunamis affecting coastal regions globally. A land impact destroys cities and causes millions of casualties if it hits populated area. The 1908 Tunguska event in Siberia, where an approximately 60-meter asteroid exploded in the atmosphere, flattening 2,000 square kilometers of forest, exemplifies this scale. If Tunguska had occurred over Moscow or New York, it would have killed millions. Large asteroids, 1 kilometer diameter and above, impact Earth every 500,000 to few million years. These cause global catastrophes through a combination of direct blast effects, wildfires, tsunamis, and atmospheric dust-blocking sunlight causing crop failures and temperature drops lasting years. The dinosaur-killing Chicxulub impactor was about 10 kilometers diameter, releasing energy equivalent to billions of nuclear weapons. Even 1 to 2 kilometer asteroids release energy equivalent to hundreds of thousands of nuclear weapons and cause climate disruption severe enough to threaten agricultural civilization through multi-year impact. Winter. When I say it's impossible to stop asteroid impacts, I mean we cannot reliably prevent impacts across this full spectrum of threats. We might detect and deflect some large asteroids if we have decades of warning. But we cannot stop medium asteroids with short warning times. We cannot stop small asteroids at all. We cannot stop long-period comets from the outer solar system. We cannot stop asteroids we haven't detected yet, despite surveys. And we cannot guarantee deflection success even for known threats due to technical and resource limitations. The planetary defense capability we've achieved is far more limited than public messaging suggests. Let me start with the detection challenge, because you can't deflect asteroids you haven't detected, and despite decades of surveys, we've cataloged only a fraction of potentially hazardous asteroids. Current surveys have found approximately 95% of near-Earth asteroids larger than 1 kilometer diameter. This is impressive achievement, but the remaining 5% still represents dozens of unknown civilization-ending asteroids that could hit without warning, and for smaller but still dangerous asteroids, the detection rates drop dramatically. For asteroids 140 meters and larger, estimated to be about 25,000 objects in near-Earth space, we've cataloged only about 40%, meaning roughly 15,000 asteroids large enough to cause regional catastrophe remain undiscovered. Any of these could impact Earth without warning, creating disaster, killing millions. The Chelyabinsk meteor was only 20 meters diameter and injured 1,500 people. A 140-meter asteroid impacting populated area would be far worse, potentially millions of casualties. For asteroids 50 to 140 meters diameter, probably hundreds of thousands in near-Earth space, we've cataloged only a tiny fraction, perhaps a few percent. The vast majority are completely unknown. These objects impact Earth on timescales of centuries to millennia. Frequent enough to be serious threat, but rare enough that we haven't experienced major impact in recorded history, our lack of recent experience creates false sense of security that the threat is minimal or distant. Detection becomes much more difficult for smaller asteroids because they're dimmer and more numerous. Detecting objects requires they reflect enough sunlight to be visible in telescopes. Brightness falls off as square of size. So a 50-meter asteroid is 4 times dimmer than 100-meter asteroid of same composition. And small asteroids are far more abundant following power law size distribution, where number increases dramatically as size decreases. This combination of dimness and abundance means comprehensive detection of sub-100 meter asteroids is probably impossible with any realistic survey capability. Current detection surveys use ground-based telescopes scanning the sky repeatedly, looking for moving objects. The main surveys are NASA's Catalina Sky Survey, Pan-STARRS in Hawaii, and the Atlas system. These detect asteroids approaching Earth from certain angles, but miss objects approaching from the direction of the sun because they're only visible during daylight when they're overwhelmed by solar glare. The Chelyabinsk meteor approached from sunward direction and was completely undetected until it exploded in atmosphere. Proposed improvements include space-based infrared telescopes like the NEO Surveyor mission, which would detect asteroids by their thermal emission rather than reflected sunlight. Infrared detection works in all directions, including sunward, and is more sensitive to dark asteroids that reflect little visible light. NEO Surveyor could detect perhaps 65 to 70% of asteroids 140 meters and larger within a decade of operation. This is substantial improvement, but still leaves tens of thousands of dangerous asteroids undetected. Even with perfect detection, the warning time is limited by how far in advance we detect objects. Asteroids in orbits that pass near Earth return periodically, but with intervals ranging from years to centuries depending on their orbits. We might detect an asteroid on one pass and calculate that it will impact Earth on a subsequent pass decades later. This provides maximum warning time for deflection, but asteroids discovered on their final approach before impact provide minimal warning. Some asteroid orbits are highly elliptical, with aphelion beyond Jupiter. These objects spend most of their time in outer solar system, where they're too distant and dim to detect. They become visible only during brief periods near perihelion when they pass through inner solar system. If such an asteroid is on collision course, we might detect it only months or year before impact, far too short for deflection attempts. We cannot predict these impacts more than the brief detection window because we don't know the objects exist until they appear. Long-period comets from the Oort cloud are even worse. They approach from outer solar system on highly elliptical orbits with periods of thousands or millions of years. They're completely undetectable until they enter inner solar system, typically providing only months or year of warning before potential impact. Comet nuclei travel at higher velocities than asteroids, making impacts more energetic and deflection more difficult. And comets are less common than asteroids, but still pose existential threat if one happens to be on collision course. So the detection challenge creates fundamental limitation on planetary defense. We cannot detect all threats, particularly smaller asteroids and objects approaching from sunward and long-period comets. Even with best possible detection systems, we'll have incomplete catalog and short warning times for some threats. This means surprise impacts remain inevitable. No matter how much we invest in detection, the question is only how severe and how frequent. Now let me discuss the deflection challenges that make stopping detected asteroids far more difficult than optimistic scenarios suggest. Because even when we detect an asteroid years or decades in advance and calculate it will impact Earth, actually deflecting it requires overcoming enormous technical obstacles related to the physics of orbital mechanics, the properties of asteroids, the limitations of deflection technologies, and the resources and time needed for missions. The DART mission demonstrated proof of concept for kinetic impact deflection, but this was under ideally controlled conditions against a small target with no time pressure. Real planetary defense scenarios would face far more challenging conditions with much higher failure risk. The basic principle of asteroid deflection is to change the asteroid's velocity by a small amount years before predicted impact so that its orbit shifts enough that it misses Earth instead of hitting. Earth has diameter of about 12,700 kilometers. So shifting an asteroid's trajectory by more than this distance causes miss instead of hit. Orbital mechanics means that small velocity changes applied early compound over time into large position changes. A velocity change of just 1 centimeter per second applied 10 years before impact shifts position by about 15,000 kilometers, easily enough to convert hit into miss. But achieving even these small velocity changes is difficult because asteroids are massive objects with enormous momentum. Momentum is mass times velocity. Changing momentum requires applying force over time through impulse. For asteroid deflection, we apply impulse through various methods. Kinetic impact, where we crash spacecraft into asteroid transferring momentum. Nuclear explosion near surface, creating shock that pushes asteroid gravity tractor, where spacecraft hovers near asteroid and its gravitational attraction slowly pulls asteroid off course. Mass driver or laser ablation that removes material from surface, creating reactive thrust. Each deflection method has severe limitations that make it unsuitable for many scenarios. Kinetic impact requires hitting fast-moving target across millions of kilometers. The impactor must have sufficient mass and velocity to transfer meaningful momentum, dart massed about 600 kilograms, and impacted Dimorphos at 6.6 kilometers per second. The momentum transfer changed Dimorphos' orbital period around its parent asteroid Didymos by about 32 minutes. This sounds impressive, but Dimorphos' tiny moon, only 160 meters diameter, orbiting another asteroid, not an Earth-threatening object on collision course. Scaling kinetic impact to deflect dangerous asteroid approaching Earth faces major challenges. Larger asteroids require more momentum transfer, needing either more massive impactors or higher impact velocities or multiple impacts. Launching massive spacecraft requires powerful rockets and substantial cost. Achieving high impact velocities requires either very fast spacecraft, which are difficult to guide accurately, or impacting asteroid that's already moving fast relative to Earth, which limits available targets. The momentum transfer efficiency depends critically on asteroid properties, particularly its internal structure and composition. Solid monolithic asteroids transfer momentum efficiently, with most of impactors' kinetic energy going into changing asteroid velocity. But many asteroids are rubble piles, consisting of loosely bound fragments held together by gravity. Impacting rubble pile might cause it to fragment or might bury the impactor without efficient momentum transfer. We often don't know asteroid structure until we visit, which might be too late. Some asteroids are binary systems, with a small moon orbiting the main body like Didymos Dimorphos. Impacting the main body might disrupt the binary, causing unpredictable orbital changes. Some asteroids rotate rapidly, which complicates targeting and momentum transfer. Some have irregular shapes, creating uncertainty about impact, location, and effects. All this variability means kinetic impact success is uncertain until attempted. Nuclear deflection involves detonating nuclear weapon near asteroid surface. The X-rays and plasma from explosion, heat, and vaporized surface material creating high-pressure gas that pushes asteroid. Nuclear explosions are far more energetic than kinetic impacts, allowing deflection of larger asteroids with single device. A megaton-class nuclear weapon detonated optimally could deflect kilometer-scale asteroid if done decades before impact. But nuclear deflection faces severe technical and political obstacles. Determining optimal detonation height and position requires understanding asteroids' shape and composition and rotation. Detonating too close risks fragmenting asteroid, creating multiple impactors instead of one. Detonating too far reduces efficiency as expanding fireball energy dissipates. We've never tested nuclear deflection on actual asteroids, so performance predictions are uncertain. Politically, launching nuclear weapons into space violates outer space treaty provisions against nuclear weapons in space, though exceptions might be made for planetary defense. Developing and deploying nuclear deflection system requires international cooperation because many nations would need to approve. During Cold War, any nuclear launch might be misinterpreted as attack triggering nuclear war. Even today, mistrust and verification challenges complicate nuclear deflection planning. Nuclear deflection requires delivering weapon to asteroid which might be millions of kilometers away. Existing nuclear weapons are designed for terrestrial targets, not space missions. Adapting warheads for space requires radiation hardening and thermal protection and reliable detonation systems. Developing and testing these systems costs billions and takes years. Nations might be reluctant to invest in capability that might never be used or that could be perceived as weaponizing space. Gravity tractor deflection uses spacecraft hovering near asteroid, relying on mutual gravitational attraction to slowly pull asteroid off course. This is an extremely gentle method, avoiding risks of impact or explosion, but is also extremely slow, requiring years to decades of continuous operation to achieve meaningful deflection. The gravitational force between spacecraft and asteroid is tiny. For 1,000 kilogram spacecraft hovering 100 meters from 100,000-ton asteroid, the force is about 0.0007 newtons. Accelerating the asteroid at this rate takes many years to achieve even centimeter per second velocity change. Gravity tractor requires maintaining precise position near asteroid for extended periods. This demands sophisticated navigation and propulsion systems with high reliability. Any system failures during multi-year mission cause mission failure. The spacecraft must carry sufficient propellant for station keeping over years or use ion drives with high specific impulse but low thrust. Ion drives require electrical power from solar panels or nuclear reactors, adding mass and complexity. For larger asteroids or shorter warning times, gravity tractor is impractical because acceleration is too slow. It works only for relatively small asteroids detected decades in advance. Even then, it requires launching massive spacecraft or multiple spacecraft to provide sufficient gravitational force. The costs and time for gravity tractor missions are prohibitive except for smallest threats with longest warning. Mass driver or laser ablation deflection involves landing systems on asteroid that remove surface material, ejecting it at high velocity, creating reactive thrust that pushes asteroid. Mass driver uses robotic mining equipment to excavate material and electromagnetic launcher to throw it off asteroid. Laser ablation uses high-power laser to vaporize surface, creating plasma jet. Both methods provide continuous low thrust over extended periods, potentially accumulating significant velocity change. But landing on asteroid is extremely difficult because most asteroids have irregular shapes and unpredictable gravity fields and are rotating. Achieving soft landing requires detailed reconnaissance and precise navigation. Anchoring equipment to surface is challenging because surface might be loose, regolith, or solid rock, or something in between. We don't know until we try. The OSIRIS-REx mission found asteroid Bennu's surface much more pebble-like than expected, requiring mission plan changes. Operating mining or laser equipment on asteroid surface requires power from solar panels or nuclear sources. Equipment must function reliably in vacuum and temperature extremes for years without maintenance. Removing material efficiently requires understanding material properties which vary between asteroids. Some are metallic, some are rocky, some are carbonaceous. Equipment designed for one type might fail on another. The mass removal rate must be sufficient to achieve required velocity change within available time. This might require removing thousands or millions of tons of material, depending on asteroid size and warning time. Scaling up to these rates requires enormous equipment masses that are difficult to land and operate on asteroid. The whole enterprise becomes comparable in complexity to asteroid mining operations, which face their own severe economic and technical challenges, as I've discussed in other contexts. So, examining deflection methods, each has narrow applicability and significant failure risks. Kinetic impact works for small to medium asteroids with decades of warning and favorable properties. Nuclear deflection works for larger asteroids but faces political and technical barriers. Gravity tractor works only for small asteroids with very long warning. Surface operations require capabilities we haven't demonstrated and might not be feasible for many asteroid types. There's no universal deflection method that reliably works for all threat scenarios. Now let me discuss the warning time problem in much greater detail, because this is perhaps the most fundamental limitation on planetary defense. The effectiveness of all deflection methods depends critically on having years or preferably decades of warning. But many impact scenarios provide much shorter warning, making deflection impossible regardless of our technical capabilities. As I mentioned earlier, asteroids approaching from sunward direction are difficult to detect until they're very close. Long-period comets appear with only months of warning. And even known asteroids can have orbital uncertainties that prevent confirming impact trajectory until relatively late. Orbital mechanics calculations show that small velocity changes compound into large trajectory shifts given sufficient time, but the required velocity change increases dramatically as warning time decreases. If we have 20 years warning, we might need to change asteroid velocity by 1 centimeter per second to achieve miss. If we have 10 years, we need 4 centimeters per second. If we have 5 years, we need 16 centimeters per second. The scaling is roughly quadratic with time because distance traveled goes as time squared for constant acceleration. At some point, the required velocity change exceeds what our deflection methods can provide. Kinetic impact has practical limits, around 1 to 10 centimeters per second, depending on impactor mass and number of impacts we can deliver. Nuclear deflection might achieve 10 to 100 centimeters per second, but with high uncertainty and fragmentation risk, gravity tractor is limited to fractions of centimeter per second, even with multi-year operations. When required velocity change exceeds these limits, deflection becomes impossible. For warning times less than about 5 to 10 years, most deflection methods become marginal or impractical. For warning times less than 1 to 2 years, deflection is essentially impossible, except perhaps for very small asteroids using nuclear methods with high fragmentation risk. And for warning times measured in months or weeks, nothing we can do prevents impact. We're reduced to evacuation of impact zone if we know where it will hit, and hoping for minimal casualties. The DART mission succeeded because it was not operating under time pressure. Mission was planned over many years, launched in November 2021, and impacted Dimorphos in September 2022 after 10-month cruise. The target was small moon in known orbit around larger asteroid, allowing precise targeting. This is idealized scenario, completely unlike real planetary defense, where we might detect threat with short warning and must mount rapid response with minimal planning time. Rapid response requires maintaining standing infrastructure of deflection capabilities ready to launch on short notice. This means designing and building spacecraft in advance and storing them in readiness, maintaining launch vehicles and mission teams and ground systems. All of this is extremely expensive if systems are never used, and if we optimize for rapid response, we sacrifice performance because we can't customize mission to specific threat. The alternative is designing and building custom deflection mission after detecting threat. This provides optimized performance for specific asteroid, but requires months to years of development and testing time. By the time mission is ready, threat might be too close for effective deflection. This is classic trade-off between readiness and optimization that has no perfect solution. Political decision-making adds additional delays to already tight timelines. Once threat is detected and confirmed, someone must authorize deflection mission. This requires international coordination because asteroid orbits are global threat, not confined to one nation. Developing consensus on mission approach and resource allocation and risk acceptance takes time, especially if nations disagree about threat severity or preferred methods. During the delay, while politicians debate and bureaucracies process decisions, the asteroid continues approaching and deflection becomes progressively more difficult. What might have been straightforward deflection with immediate action becomes marginal or impossible after delays. The political and organizational challenges might be as limiting as technical challenges for planetary defense. There's also risk of false alarms, where initial orbit calculations suggest impact, but refined observations show miss. The social and political cost of mobilizing planetary defense for false alarms is high. Crying wolf repeatedly undermines support for actual threats, but waiting for absolute certainty before acting reduces available response time. Managing this trade-off between false alarms and timely response is extremely difficult. The 99942 Apophis asteroid illustrates these challenges. When first discovered in 2004, initial orbital calculations suggested 2.7% probability of Earth impact in 2029. This triggered major concern and media attention. Further observations refined orbit, and by 2005, impact probability was reduced to essentially zero. But for a period of months, there was serious discussion of deflection missions, despite substantial uncertainty. If we had launched deflection attempt and later observations showed it was unnecessary, we'd have wasted billions on false alarm. Conversely, waiting too long for certainty risks missing deflection window. With Apophis, we had luxury of many years to refine orbit before potential 2029 close approach. But asteroid discovered with shorter warning might require deciding whether to attempt deflection before orbit is precisely determined. Deflecting asteroid that would have missed naturally is waste, and might even cause it to impact through deflection errors. Not deflecting asteroid that will hit because we're waiting for more data is catastrophic. So warning time limitations create fundamental constraint on planetary defense. Many impact scenarios provide insufficient warning for effective deflection regardless of our technical capabilities. We might detect threat too late, or face political delays, or need time for orbital refinement. All of these factors eat into available response time, making deflection marginal or impossible. This is not a problem that better technology solves, because it's about physics of orbital mechanics and organizational realities, not engineering capabilities. Now let me examine the resource and economic constraints on planetary defense in detail, because even if we had perfect detection and unlimited warning time, actually deflecting dangerous asteroids requires enormous resources that must compete with other priorities and limited government budgets. And the cost-benefit analysis of planetary defense is complicated by the low probability, high consequence nature of the threat. Developing and maintaining comprehensive planetary defense system requires sustained investment over decades in detection surveys, mission design and development, launch and operations infrastructure, international coordination, all funded by governments that face many competing demands for limited resources. Current planetary defense funding is roughly $150, $200 million per year globally, mostly from NASA with smaller contributions from ESA and other space agencies. This funds telescopic surveys and technology development and missions like DART. It's modest investment compared to overall space budgets, but still requires justification to political leaders and publics who might question spending hundreds of millions annually on threat that might not materialize for centuries. Comprehensive planetary defense would require far more investment, completing NEO-Surveyor to improve detection costs about $1.2 billion. Developing and maintaining standby deflection capabilities might cost several billion dollars for spacecraft development and testing and operational readiness. International coordination and decision-making infrastructure requires ongoing funding for organizations and planning exercises and communication systems. Total cost for robust planetary defense system might be $10 billion over a decade for initial development, plus billions per year for ongoing operations and surveys. This is comparable to cost of major scientific programs like the James Webb Space Telescope or large particle accelerators. It's not prohibitive in absolute terms, but requires sustained political will to fund preventive measures for low probability threats. The challenge is that asteroid impacts have very low annual probability but very high consequence. If they occur, a civilization-ending 10-kilometer asteroid impacts Earth roughly every 100 million years on average. So annual probability is about 0.0000001%. Even regional catastrophe, scale 100-meter asteroids impact only every few thousand years. Annual probability about 0.01 to 0.03%. These are extremely low probabilities that make planetary defense seem low priority compared to problems with higher probabilities. But the consequences are so severe that expected value calculation still favors defense investment. Expected value equals probability times consequence. For civilization-ending impact with probability 10, -6 per year and consequence of $10 trillion or more in damages plus billions of deaths, expected annual value is millions or billions of dollars. This suggests optimal investment in prevention is millions to billions per year, comparable to current spending. However, political systems are notoriously bad at addressing low probability, high consequence risks, especially when timescales are long. Politicians respond to immediate visible problems that affect voters, and near-term spending on asteroid defense provides no visible benefits in most years because no impact occurs. It's easy to cut planetary defense budgets when funds are needed for more immediate priorities, and maintaining funding across multiple political administrations over decades is extremely difficult. The benefits of planetary defense are also difficult to measure because success means nothing happens If we deflect asteroid that would have caused catastrophe, we save countless lives and prevent enormous damage. But from public perspective, we spent billions on space mission and nothing happened. It's hard to prove that impact would have occurred without deflection versus natural miss. Skeptics can always claim we wasted money on threat that wasn't real. This creates asymmetric accountability, where failure to prevent impact is highly visible catastrophe that would be blamed on inadequate planetary defense, but success in preventing impact is invisible non-event that generates no political credit. This asymmetry discourages investment because politicians bear all downside risk of being blamed for inadequate defense, but receive no upside reward for successful prevention. International coordination adds another layer of resource challenges because planetary defense requires global cooperation to be effective. Asteroids don't respect national boundaries. Deflection of asteroid on course to impact one country might cause it to impact different country. If deflection is imprecise, this creates complex liability and decision-making issues about who authorizes deflection and who bears costs and risks. Developing international frameworks for planetary defense requires diplomatic efforts and treaty negotiations and institutional development. The United Nations has established International Asteroid Warning Network and Space Mission Planning Advisory Group to coordinate international response, but these are planning bodies without operational capabilities or funding authority. Actually implementing international planetary defense requires nations to commit resources and cede some sovereignty over decision-making. Smaller nations might free ride on planetary defense provided by larger nations. Since everyone benefits from deflection regardless of who pays for it, this creates collective action problem, where optimal global investment exceeds what any individual nation is willing to contribute. Overcoming this requires international cost-sharing agreements that are politically difficult to negotiate and enforce. The history of international climate negotiations shows how challenging this is even for more immediate threats. So resource and economic constraints create serious limits on planetary defense. Sustained funding is politically difficult for low-probability threats. Benefits are invisible when successful, creating accountability asymmetry. International coordination faces collective action problems and sovereignty concerns. These factors mean that actual planetary defense capabilities will likely remain far below what would be technically optimal. We won't invest enough to address all threats because political and economic realities constrain what's feasible. Now let me discuss the technical uncertainties and failure modes that make deflection unreliable even when attempted with adequate resources and warning time, because asteroids are diverse objects with variable properties that we often don't understand well until we visit them, and space missions are complex systems with many potential failure points. Even well-planned deflection attempts have substantial probability of failure that makes planetary defense less reliable than optimistic scenarios suggest. Asteroid physical properties vary enormously, affecting deflection effectiveness. Composition ranges from metallic nickel iron and M-type asteroids to rocky silicates and S-type to carbonaceous materials and C-type. Density varies from about 1.3 grams per cubic centimeter for carbonaceous to 7 to 8 grams per cubic centimeter for metallic. Structure ranges from monolithic solid bodies to rubble piles held together loosely by gravity. Surface properties range from bare rock to loose regolith to boulder fields. Rotation periods range from hours to weeks, and shapes vary from nearly spherical to highly elongated or contact binary. All of these properties affect how asteroids respond to deflection attempts. Kinetic impact momentum transfer depends on crater formation, which depends on surface strength and composition. Solid rock creates different crater than loose regolith. Metallic asteroids respond differently than carbonaceous. Fast rotation complicates targeting and might affect momentum transfer efficiency. Irregular shapes create uncertainty about impact, location, and effective target area. We can measure some properties from Earth through spectroscopy and radar and photometry, but precise characterization requires spacecraft visits. This creates chicken and egg problem, where we want to know properties before designing deflection mission, but we need deflection mission to visit asteroid and measure properties. The solution is sending reconnaissance mission first, but this adds time and cost that might not be available for rapid response. Even with reconnaissance, there are surprises. The OSIRIS-REx mission to asteroid Bennu-discovered surface was far more boulder-rich and loose than expected from Earth observations. This required changing sample collection strategy and created challenges for touching surface. Similar surprises during deflection mission could cause mission failure. Impactor might bounce off unexpectedly hard surface or sink into unexpectedly soft regolith. Actual momentum transfer might differ substantially from predictions. Rubble pile asteroids are particularly problematic for deflection. These are loosely bound aggregate of fragments with voids and weak internal structure. Impacting rubble pile might cause it to fracture, creating multiple fragments instead of deflecting unified body. If fragments remain gravitationally bound, they might reaccumulate after impact. If fragments separate, they create multiple impactors on slightly different trajectories, some of which might still hit Earth. We've converted single impact into multiple impacts, which might be worse outcome. Nuclear deflection of rubble pile risks catastrophic fragmentation, where explosion energy exceeds gravitational binding energy. This shatters asteroid into many fragments that disperse. If this occurs years before predicted impact, the fragments might spread enough that most miss Earth. But if it occurs close to Earth, the fragment stream might all impact, creating devastating bombardment. The Tunguska event might have been fragmenting comet or asteroid that exploded in atmosphere. Similar fragmentation in space could create similar shower. Mission technical failures can occur at any stage of deflection attempt. Launch vehicle failure prevents spacecraft from reaching space. This occurs about 2 to 5% of launches historically, though rates have improved recently. Spacecraft systems failures during cruise phase could cause loss of mission. These include power system degradation, propulsion problems, navigation errors, computer malfunctions, communication failures. Each subsystem has failure probability that compounds over multi-year missions. Approach and targeting phase is critical for kinetic impactor. Spacecraft must navigate to precise intercept trajectory, matching asteroids' position and velocity at moment of impact. Navigation requires accurate knowledge of asteroid orbit and real-time tracking and trajectory corrections. Errors in any of these create impact location errors. DART demonstrated successful targeting, but target was large moon in well-known orbit. Hitting smaller asteroid on first encounter with less prior knowledge would be more difficult. Post-deflection orbit determination requires measuring asteroid's new trajectory to verify deflection succeeded and impact is prevented. This requires continued observation over weeks or months. As asteroid moves in its altered orbit, measurement errors create uncertainty about whether deflection was sufficient. If asteroid remains on marginal trajectory, we might need second deflection attempt with even less time, cascading from initial deflection that was insufficient. Multiple deflection attempts might be necessary for large asteroids or short warning times where single mission doesn't provide enough velocity change. Coordinating multiple spacecraft arriving sequentially requires sophisticated mission planning and reliable operations. Each additional mission multiplies failure probabilities and costs. And if early missions fail or are insufficient, later missions might not have time to compensate. The cumulative probability of mission success through all these stages might be 70 to 90% for well-planned mission under ideal conditions. This sounds reasonably good, but means 10 to 30% failure rate, given that we might only get one attempt at deflecting civilization-ending asteroid. 10 to 30% failure probability is sobering. It's not reliable planetary defense, but is high-stakes gamble with civilization's future. Now, I want to explore in much greater depth what the impossibility of comprehensively stopping asteroid impacts means for how we should think about existential risks, planetary defense policy, and humanity's long-term vulnerability to cosmic threats that we cannot fully control. The recognition that asteroid impacts remain largely unavoidable despite our technological capabilities is profoundly important because it reveals fundamental limits on human agency in the universe. We cannot protect ourselves completely from cosmic hazards through technology and planning. Some threats remain beyond our control, requiring acceptance and resilience rather than prevention. This is psychologically difficult because it contradicts the narrative of human mastery over nature that has dominated Western thought since the Enlightenment. We've become accustomed to believing that science and technology can eventually solve any problem, that through sufficient knowledge and effort we can control our environment and protect ourselves from threats. Asteroid defense seemed like natural extension of this capability, using our understanding of physics and orbital mechanics to prevent impacts, just as we prevent diseases through medicine or prevent floods through engineering. But the asteroid threat reveals that some problems are beyond comprehensive solution. We can reduce risk through detection and deflection efforts, but we cannot eliminate it. We remain vulnerable to surprise impacts from undetected objects, to long-period comets arriving with minimal warning, to deflection mission failures, to political failures preventing timely response. The threat is inherent in living on a planet and solar system filled with debris that occasionally strikes planetary surfaces. It's not an engineering problem we can solve, but is a cosmic condition we must accept. This recognition should inform how we allocate resources for planetary defense and how we communicate about the threat to publics and policymakers. Rather than promising comprehensive protection that we cannot deliver, we should be honest about the limitations of planetary defense and frame it as risk reduction, not risk elimination. We can decrease probability of catastrophic impact through detection and deflection capabilities, but we cannot make probability zero. Some residual risk remains no matter what we do. The expected value calculation still favors investing in planetary defense because even partial protection has enormous value given the magnitude of potential consequences. Spending billions to reduce civilization-ending impact probability from once per 100 million years to once per 200 million years sounds marginal, but represents enormous expected value in prevented deaths and damages, and the benefits compound over time as civilization persists for longer periods with reduced threat. But we should be realistic about diminishing returns from planetary defense investment. The first billion spent on detection and basic deflection capability provide large risk reduction, moving from zero capability to modest capability. Additional billions provide smaller incremental improvements as we reach limits of what's technically feasible. There's optimal investment level beyond which additional spending produces minimal additional safety. We need to find this level through careful analysis rather than assuming unlimited spending is justified. We should also recognize that planetary defense competes with other existential risk mitigation efforts for limited resources. Nuclear war and engineered pandemics and unaligned artificial intelligence and climate change all pose existential or catastrophic risks that might have higher probabilities than asteroid impacts, even if lower individual event. Consequences. Optimal allocation of existential risk reduction spending requires comparing expected values across different threats and investing where marginal risk reduction per dollar is highest. Asteroid impacts might not be the highest priority for existential risk reduction despite the visceral nature of the threat. Nuclear war has much higher probability, especially during periods of geopolitical tension. Engineered pandemics could become more probable as biotechnology advances. AI alignment failures might pose catastrophic risks within decades if artificial general intelligence is developed without adequate safety measures. Climate change is already causing damages and will worsen this century. These threats have higher near-term probabilities than asteroid impacts. But asteroid defense has advantages that make it worth sustained, moderate investment. The threat is well understood physics with clear mitigation approaches. There is international consensus that asteroid defense is legitimate priority without the political complications of nuclear disarmament or AI governance. The technologies developed for planetary defense have spillover benefits for space science and exploration, and asteroid defense is existential insurance against low probability but absolutely catastrophic tail risk that would end civilization if it occurred. So a reasonable planetary defense strategy involves sustained investment at moderate levels, roughly current spending of hundreds of millions annually for detection and technology development, with capability to rapidly scale up spending if serious threat is detected requiring deflection mission. This provides good baseline protection